Hello and welcome to another review video. All right, so this one's going to focus more on questions that you're likely to see on the multiple choice section of the exam. So these aren't really like big, long, open-ended questions. They're more kind of shorter, short answer, multiple choice type questions that you could see. So number one, a study is conducted to determine if one can predict a student's grade based on the number of hours they study. The response variable in this study is what? All right. So generally, when you have an experiment, you have an explanatory variable and you have a response variable. So the explanatory variable in this case would be hours of study. And then we're using that to hopefully understand how a student's grade responds to that variable. So our response variable is going to be the student's grade. Whoops. So the general idea is being able to look at a situation and differentiate between an explanatory variable and a response variable. And basically you just have to ask yourself, is the student's grade explaining the hours of studying, or is the hours of studying explaining the student's grade? And I think most people would understand that the amount of time you spend studying is going to help explain the grade that you ultimately achieve. All right, number two, suppose we fit the least squares regression line to a set of data. What should we conclude if the residuals show a curved pattern? All right. So this is basically knowing how to read residuals and what they mean. So ideally, there should be no pattern to the residuals. So in this case, the linear model, which is what regression is a bad choice. All right, so again, residual plots usually look like this, and you've got points scattered all about. If you've got something like this is good. This is no pattern. All right, if you've got something like this where you're seeing like a pattern to the dots, all right, this would be bad. All right, this suggests you should not use a linear model. This one says your linear model was an appropriate choice, right? But kind of understanding a residual plot and knowing how to interpret one. Number three, a political analyst developed a regression model that tries to predict the chance of a presidential candidate winning the election based on the average percent of vote across the primaries. The equation of the least squares regression line was y hat equals 10 plus 0.9x, where y hat represents the predicted chance of winning, and x is the average percent of vote across the primaries. Suppose Mark Van Buren gets 75% of the vote during the primaries. What's his predicted chance of winning? All right, so this is really a pretty simple problem. It's just taking this 75 and plugging it in for x. I mean, it's kind of hidden behind like talk of regression and predictions and all of this, but at the end of the day, it's really just plugging that number into your formula. So y hat equals 10 plus 0.9 times 75. So if we work that out, y hat ends up being, let's see, 0.9 times 75 plus 10, 77.5. All right. So again, don't get overwhelmed or intimidated by something like this. It's really as simple as just, all right, take this value, plug it in for x. And this is the prediction that the regression equation would produce based on the data that you provided. All right, there is a positive correlation between the amount of doctors in an area and the death rate. Does this mean that you can live longer by moving to a location with fewer doctors? Why or why not? All right, So this is just one of the big lessons of any statistics course. And it would be no correlation does not equal causation. All right. Doctors are not causing people to die more, are not causing more deaths. There's likely a lurking variable, in this case sickness, that is causing both variables to move. In the same direction. So it's not that the doctors are causing sickness, it's that more sickness causes more doctors to show up, and more sickness causes more deaths. So again, doesn't mean we can, the only way we can ever establish causation is with a well-designed experiment. Just observing that areas with more doctors have a higher death rate is not enough to say that one causes the other. And hopefully this one's like a pretty obvious example, but it can show up in more subtle ways as well. Number 5, the correlation between the age and weight of bunnies is found to be about 0.6. Suppose we use the age of a bunny X to predict the weight of a bunny Y. What fraction of the variation in weights could we explain with a least squares regression line? So this is vocabulary. And fraction of variation in the weights is another way of saying what is the R squared value. So if you understand what this question's asking, it becomes pretty trivial. So R squared, they told us that the correlation was 0.6, so 0.6 squared, so that gives us a value of 0.36. All right, so trivial question as long as you understand what that is actually asking for. All right, number 6, we divide the company into 2 groups, first-year employees and others. Then we take random samples from each group. This is an example of what type of sampling. All right, so we're assuming that these 2 groups have differences. So we're dividing them up into separate groups and taking samples from each of those groups. We call that a stratified random sample. All right, we talked about this a lot in class, but the example I would always give is it's like dividing our school into freshmen, sophomore, juniors, and seniors. Each group is slightly different, so we want to make sure that we're hitting up all of those groups. Same idea here. First year employees versus other employees. We're dividing those into separate groups to make sure we get representation from both. All right, so that's called a stratified random sample. And you should be familiar with terms like stratified random sample, cluster sample, census, simple random sample, and just what each of those are. Number 7, in a simple random sample of size n, what probability should every member of the sample have of being selected? So if it is a simple random sample, everyone should have an equal chance of selection. And if there are n people in total, that implies that each person's chance should be 1 over n. All right, but that's understanding that a simple random sample requires that everybody has an equal chance. And then once you know that, it's just saying, all right, well, if there's 10 people, everyone has a 1 in 10 chance. If there's 100 people, everybody has a 1 in 100 chance. But everybody has an equal chance of being selected. In an experiment, what do we call an observed effect so large that it would unlikely to have happened by chance? All right, so it's exceeding the bounds of sampling variation. So It's exceeding what we would expect from sampling variation. And the term that we have for that is that it is statistically significant. All right, so when we say something is statistically significant, what we're saying is that the observed effect was so large that it's probably not just sampling variation, it's probably not just random fluctuations, it's probably indicative of some actual, thing that we're trying to measure or examine. Right? But statistically significant is the term that we're looking for there. All right, last but not least, a small city wants to conduct a survey about satisfaction with municipal services. They divide the city into blocks, randomly select 20 blocks, and then survey every person in those 20 blocks. How would you describe this sampling method? All right, so this is different than number 6. In number 6, we divided the groups by some characteristic and then surveyed separately from each group. In this one, we basically tried to make little mini groups that represented the entire population. All right. So when I always used my school example, stratified sample is dividing each grade, 9th grade, 10th grade, 11th grade, 12th grade. This, which is called cluster sampling, is where you would divide the building by wings and say, all right, we're just going to survey the 100 wing because chances are the 100 wing currently has a little bit of everything in it. Or we're just going to survey the 300 wing. And sometimes this is logistically easier because you're just saying, okay, I just survey everybody in the 300 wing and I'm done. It's easy. Everybody's in one spot. And it should be representative as long as those are, as long as each wing has a little bit of each group in it. So generally the rule or the little rule of thumb that we say for these is that a cluster sample is different within, like each group is different within, but the same across different groups. Versus the stratified is the same within, but different across the different stratas. So each group is the same inside 9th grade, 10th grade, 11th grade, 12th grade, but each group is different. Here, each group has a little bit of everything in it, but there's really not that much difference between the 100 wing and the 200 wing, all right? The different groups that you've created are sort of interchangeable, but each group has a lot of diversity inside of it. Here, the groups don't have a lot of diversity inside of it, but each group is very different, all right? And that's kind of how you have to try to keep them separate in your head, all right? So again, these are things that can show up on the multiple choice part of the exam. So you could imagine a question where I give you a scenario and then ask you what type of sample it is. Definition stuff like statistically significant, recognizing terms like this and associating that with your R squared values, bigger ideas like correlation and causation, using a regression equation, understanding residuals, understanding the idea of an explanatory versus a response variable. All right, so all stuff that's fair game, all stuff that you could expect to see on the short response part of your exam. All right, so as always, let me know if you have any questions. Otherwise, I'll see you when I see you.